decided to put 7.1 and 7.2 into two separate videos, though they very easily could have been one video. I just decided that shorter videos this week might be nice since last week's were really long. So today we're going to talk about uniform probability distribution, graphing a normal curve, stating the properties of a normal curve, and explaining the role of area in a normal density function. So we've been talking about bell curves and normal curves and empirical rule a lot already this term. And we're going to continue along that vein. So we're going to take a step away from the binomial probability distribution. And I probably will do a really short video explaining the difference between the normal probability or the normal density function and the binomial probability distribution. So when you get to the test, you'll know exactly what to look for with the different questions. All right, so let's get rolling. So a uniform probability distribution, it's a really small part of it, but it is probably one of the things the students miss the most. So look at the word uniform. This is really important. Think about what the word uniform means. Things that are uniform, they're all pretty much the same. So here is an example of a problem with a uniform probability distribution. Imagine you have a friend that's always late. You might be that friend. I don't know. So let the random variable x represent the time from when you're supposed to meet your friend until he shows up. Suppose your friend could be on time, which would be x equals 0, or up to 30 minutes late, which would be x equals 30. All intervals of equal time between x equals 0 and x equals 30 are equally likely. So, for example, it's just as likely for your friend to be 3 minutes late or 4 minutes late as it is for him to be 25 minutes late or 26 minutes late. So this is all equally likely. So the random variable x can be any value in the interval from 0 to 30. That is 0 is less than or equal to x or less than or equal to 30. Any two intervals of equal length between 0 and 30 are equally likely to happen. They follow a uniform probability distribution. So if any value in between is equally likely to happen, that follows a uniform probability distribution. So let's look what that looks like on a graph in just a second. So the probability density function. So this is really important. This is for things that are uniform and for things that are not uniform. So the total area under a graph, all the possible values together, when you add them all up, when you add all of those values together, they're going to add up to 1. All of the values together, all the possibilities underneath that curve, they add up to 1. And the height of the graph, of any part of the graph, the height of that graph has to be greater than or equal to 0 for all the values of the random variable. So every value has a probability that is greater than or equal to 0. So let's take a look at the graph of that uniform density function that we just talked about. The uniform probability distribution we just talked about. So here's the graph. Our random variable is time, that would be on our x-axis, and density, which is our probability of it happening, is on the left side. So because the probability is equally likely to happen, and the area underneath that curve must be 1, because these are all of the values from 1 to 30. So pretend those 30 little dots there. So between 0 and 1, 0 and 1 minute late, it has a 1/30th chance of happening because each of those values has the same probability, and there are 30 values between 0 and 30. So they have the equal probability of happening. Okay, so let's move on. So let's talk about what is the probability that your friend would be between 10 and 20 minutes late. So let's look at this. So here's my graph. So 10 minutes is right here and 20 minutes is right here. So there's a 10-minute time frame here. So this right here, this is 10 because 20 minus 10 is 10. So the length of this side of this rectangle is 10. And we know that the height of this rectangle right here, that height is 1/30. So it is 10 a.m. There's a 20% chance probability. Oops, sorry, we'll go back here. So what we do is we're going to take that 10. We're just going to find this area right here. This area right here is going to give us the probability that they're going to be between 10 and 20 minutes late. So 10 times 1 over 30 equals 1/3. So there's a 1/3 chance, or 33.33% chance, that he'll be between 10 and 20 minutes late. So all you're doing is finding that area of that rectangle right there. Okay, so let's look at the next problem. So it's 10 a.m. There's a 20% probability your friend will arrive between how many minutes? So I know I'm looking for 0.20 equals the 1/30th times what? Times x, because we don't know how many minutes late. So x would be how many minutes it is, right? Because that's our variable. So we don't know how many minutes, so there's a 20% chance of them being how late. So I've just multiplied both sides by 30. This is just your basic math here. So 30 times 0.20 would be 6. So it's a 20% chance that he will arrive within the next 6 minutes. So this is the uniform probability. Oops. So that area, sorry, I guess I could have shown you the piece of it right there. So this is my 10 o'clock right here. And this would be my rectangle. So we needed to figure out the backwards of that, what that time would be. All right. So relative frequency histograms, we've seen these for a while here. They're symmetric and bell-shaped. The ones that are symmetric and bell-shaped are said to have a normal curve. We've been dealing with normal curves a lot already, and we're going to be dealing with them. This whole chapter is on normal curves. So this bell-shaped or symmetric graph here has a normal curve. If a continuous random variable is normally distributed or has a normal probability distribution, then the relative frequency histogram of the random variable is shape of a normal curve. So if it is normally distributed or it has a normal probability distribution, then it's going to have that bell-shaped curve. It's going to be symmetric. It's going to say we will say it has a normal curve, and therefore, so here's my mean right here, and we have our standard deviations, one on either side. This inflection point just means that it changes concavity. So notice here, hold on a second here. So notice here it's opening downward, and then at this point here it changes to where it's, if I was going to continue this, it would open upward. That's all an inflection point is. So it has its inflection points at one standard deviation away from the mean. This is our nice pretty shape here. There's not going to be questions about inflection points. This is just describing the shape. I'm not even going to go into that one. So the properties of our normal density curve. So these are properties of that normal density curve. First, it's symmetric about the mean. This means that 50% of our data is going to be above the mean, 50% of our data is going to be below the mean. The mean, median, and mode will all equal each other or be really close. It's going to have one single peak, and it's going to be at the highest point where x equals mu. So the highest point of your peak is at the mean. It has inflection points at, one of these should be plus, x minus the standard deviation, and mu plus the standard deviation, and mu minus the standard deviation. So one standard deviation on either side of the mean. It's going to have the inflection points. And as I said, I'm not going to ask you questions about that inflection point. The area under the curve is 1. So when I add all of the values together, or all of the probabilities of each value occurring together, it's going to equal 1. This is the same thing with our probability distribution tables. When we had those tables and everything had to add to 1, it's the same thing. The area under the curve to the right, the right of mu equals the area under the curve, the left of mu, which equals 1/2. So 1 and 5 kind of are the same thing. They're just worded different. have a little bit slightly different meaning. So this is our properties of the normal density curve. We're going to be doing a lot of calculator work with this in the 7.2. This is just kind of the background information and all of the foundational stuff. Let's move on. Okay, as x increases without bound, gets larger and larger and larger, the graph approaches but never reaches the horizontal axis. And as x decreases without bound and gets more and more negative, the graph decreases but never reaches the horizontal axis. So let me show you this. Okay, so let me just draw a quick picture here. So you guys remember asymptotes? I think Math 95 probably talked about them. So when we have, so here is our bell-shaped curve. That one actually is not too bad. So you notice how with this, it's going to get closer and closer and closer to that 0, but it is never going to touch it. It just gets closer and closer and closer. It never touches that asymptote because remember, the height at any point along that graph has to be greater than 0. So if that height is greater than 0, it never touches that axis. So the empirical rule, you already know the empirical rule. So about 68% of the area is within 1 standard deviation of the mean. 95% of the area is between 2 standard deviations of the mean, and about 99.7% is within 3 standard deviations of the mean. So here is our empirical rule, our normal distribution. You've seen this over and over and over before. It's going to apply to what we are doing now also. We're going to be working directly with the graph, and it will apply to what we are doing now. It does not go away. This sticks with us through the whole thing. Okay, let me move on. So the data on the next slide represents the heights in inches of a random sample of 52-year-old males. We're going to draw a histogram of the data using a lower class limit of the first class equal to 31.5 and a class width of 1. Do you think that the variable, the height of a 2-year-old male, is normally distributed? Most things in nature seem to be somewhat normally distributed, and it's pretty cool that nature works that way. And so I would say probably. So I'm going to show you that data. Here's the data. I'm not making you do all the calculations with it. I'm not going to make you make that histogram. I don't make you do those by hand in general. Usually I make you do one and then don't make you do it again. And this is not the one I'm going to make you do. I'm going to show you mine. There we go. So this looks like a pretty normal distribution. It looks pretty nice and normal. It's bell-shaped, so I could draw my curve over it. I've got my inflection points right around about there. Those probably about 1 standard deviation away from the mean. It looks nice and pretty. So I'm going to draw a normal density curve over the histogram. So what we're going to look at now is the area of the rectangle corresponding to the height between 34.5 and 35.5. So take a look at this rectangle right here. So how do you think that rectangle, the area of that rectangle corresponds to the height here? So if I cut this little piece off and I could put that little piece under here, it would be really close to covering that entire height. So this area right here also represents the probability of finding a randomly selected child being in between 34.5 and 35.5. So it is really, it is basically the same thing. The area under that curve is also the probability of a randomly selected child being that height. So that area under that curve, once again, is the same as the probability of a child, randomly selected child, being that height. That's what that relationship is. So let's talk about that area under a normal curve. So suppose that a random variable x is normally distributed with a mean mu and a standard deviation of sigma. The area under the normal curve for any interval of the values of the random variable x represents either the proportion of population with the characteristics described by the interval of values, or the probability that a randomly selected individual from the population will have the characteristics by the interval of values. So you could either say it is the proportion or is it a probability. It is the same thing. That proportion and the probability are the same thing. So it's basically like the relative frequency and the probability, the proportion, it's the same thing. I'm going to give you an example, and I'm hoping this helps clear it up a little bit. So let's look at giraffes. The weights of giraffes are approximately normally distributed with a mean mu equals 2,200 pounds and a standard deviation sigma equals 200 pounds. We're going to draw a normal curve with the parameters labeled. We're going to shade under the normal curve to the left of 2,100 pounds. So suppose that the area under the normal curve to the left of x equals 2,100 is 0.3085. We're going to provide two interpretations of this result. So let's take a look. So here's my curve. So what I have right here is this is my mean right here. This 2,200 is my mean. And my standard deviation is 200 pounds. So one standard deviation away from the mean is there. Two standard deviations away from the mean is there. I can go on the other side as well. And I'm going to shade. So here's 2,100 and down. So I've shaded in that area. So I'm looking for this area under the curve. So this area right here is also going to represent the probability of finding a giraffe of 2,100 pounds. So here are my two interpretations. Since I know that this is my area that was given to me, the proportion of giraffes whose weight is less than 2,100 pounds is 0.3085. The probability that a randomly selected giraffe weighs less than 2,100 pounds is 0.3085. So those are the two interpretations. They mean the same thing. It just depends on the question asked. So they have the same meaning. So whether it's the area under that curve, the proportion, or the probability, they mean the same thing. So that's it for this video. We're going to pick up with 7.2 and we're going to be doing some more applications of this. So if you still have a little bit of confusion, we'll be doing some more application problems in 7.2. Thank you.